In 1929, when Edwin Hubble suggested that the universe was expanding, the scientific community almost ridiculed him. A famous physicist even said it was the most absurd thing he had ever heard.
That's right.
And today, almost 100 years later, it feels like we're experiencing déjà vu, looking at data that seems just as impossible.
Exactly. History seems to repeat itself, but on an even bigger scale. For example, here's an image from the James Webb Space Telescope. It shows a galaxy that formed 13 billion years ago, almost at the very beginning of everything.
And what was the expectation? Something primitive.
Yes, something small, kind of clumsy, a proto-galaxy, taking its first steps.
And what did Webb find?
Cosmic heavyweight. A massive, bright, fully mature galaxy that simply shouldn't have been there at that time. It's like looking at a nursery photo and finding an adult in a suit among the babies.
It doesn't make sense.
None.
And from what I understand, this isn't the first time, right? Webb has been a kind of agent of chaos since it started operating, finding things that don't match our models.
No doubt he's shaking our certainties one by one, but this most recent discovery, the one we're going to discuss today, is different.
Different how?
It doesn't just affect the theory about how galaxies are formed. It affects the foundation of everything. A Nobel Prize-winning scientist summed up the situation well. He said that Webb confirmed that our understanding of the universe might be, fundamentally wrong.
And the central problem isn't the size of a galaxy, but something even more basic. It's the rate at which the universe itself is expanding. That's it.
Exactly that. So, our goal here is to take a deep look at how the latest data from Webb is challenging two pillars of cosmology. The principle that the universe is isotropic. It's a word that sounds complicated, but the idea is simple. It's the premise that the universe expands equally and uniformly in all directions. An idea that has supported astronomy for a century.
And now, by all indications, it's wrong.
Exactly.
All right, so let's start there. What exactly is this isotropy and why has it always been so important?
Think of isotropy as a rule of cosmic fairness. It says that on large scales, the universe doesn't have a preferred direction. It doesn't matter where you look. The laws of physics are the same. Matter is distributed equally, and most importantly, the expansion of space should be the same.
So it's the assumption that the universe plays fair without favoring one side over the other.
That's right. And that's not a secondary idea, It's at the core of everything. In the Big Bang Theory, in our reading of the cosmic background radiation, our entire standard model of cosmology depends on this premise.
A foundation that seems solid until now. What has changed?
What changed was the article, published on February 6th in the Astrophysical Journal Letters. And it didn't cause a small tremor, it caused an earthquake. The conclusion of the study is shocking.
And what is the conclusion?
It's that the rate of expansion of the universe actually depends on which direction you look.
Wait, what do you mean?
In some regions of the sky, the universe is expanding faster, in others more slowly. The uniformity we used to take for granted, it simply doesn't exist.
Wow, that's dizzying. If the expansion isn't uniform, then all our calculations about the age of the universe, about its size, all of that could be wrong.
It could be drastically wrong. And I'm not the one saying this. David Gross, Nobel physicist, was very clear about the gravity of this. He said we wouldn't call this a tension or a problem, we would call it a crisis.
Crisis. When a scientist of this caliber uses that word, it means things are serious.
Very serious.
Okay. For us to understand the depth of this crisis, I think it's worth going back a bit in time to the origin of this idea of expansion. It all began with Edwin Hubble, right?
Yes, it was, in 1929. He used the largest telescope of the time and noticed something that changed everything. He saw that, with rare exceptions, all the galaxies were moving away from us.
And that wasn't all, right? The farther away the galaxy, the faster it seemed to be moving away.
Exactly. The only conclusion was that the very fabric of space was stretching, carrying the galaxies along with it. The universe was expanding.
Which led to a logical deduction. If it is growing, it was once smaller. That's it.
And if it was smaller, it had a beginning. Big Bang. The key to discovering the age of the universe would be to measure this rate of expansion, the so-called Hubble constant. With this number, we could theoretically rewind all the way back to the beginning of everything.
It sounds simple in theory, but in practice, measuring this number has become a huge headache for astronomers.
A headache is an understatement. The estimates varied absurdly. Depending on the method, the age of the universe ranged from 9.7 billion years to almost double that, 19.5 billion.
And the lowest value created that impossible paradox.
That's right, the paradox of the universe being younger than some of the stars inside it. It was like discovering that children are older than their parents. It didn't make any sense.
The hope was that, with better telescopes, the measurements would converge to a single number and put an end to the debate.
But the exact opposite happened. The more precise the measurements became, the more the results diverged.
It's as if the universe were giving two different answers to the same question. And today this dispute comes down to two main methods, right? The gold standards.
Exactly. The first method looks at the baby universe. It analyzes the cosmic microwave background, which is the echo of the Big Bang, the first light of the universe.
The Planck satellite did that, right?
Yes. Between 2009 and 2013, Planck mapped this light with incredible precision and, from this data, calculated the expansion rate. The result was approximately 67 kilometers per second per megaparsec.
Okay, just a moment. Kilometers per second per megaparsec sounds pretty technical. What does that actually mean in practice?
That's a great question. Basically, it's a measure of speed per unit of distance. A megaparsec is a huge distance, more than 3 million light years. So, a value of 67 means that for every 3.26 million light years you move away, the universe expands 67 kilometers per second faster.
I see. It's a cosmic ruler. So, that's the value we get from the past. And the second method?
The second method focuses on the mature universe, the one that's closer to us. It uses stellar beacons, Cepheid variable stars, and certain supernovas.
And how do they work?
Cepheids are amazing. They pulsate, and the rhythm of this pulse is directly linked to their actual brightness. So by measuring how fast a Cepheid pulses, we know how bright it really is.
And by comparing that with the brightness we see from here, we can calculate the distance very precisely.
Exactly. And with these distances, we measure the local expansion rate. And that's where the mystery, the Hubble tension, really deepens.
Because the result is different.
Very different. The measurements with Cepheids and supernovae reach a value of approximately 74 kilometers per second per megaparsec.
From 67 to 74. To a layperson, it might not seem like much. Because that's a cosmological abyss, not just a margin of error.
Because the precision of both methods is extremely high, the margins of error for each are very small. And the point is, they don't overlap at all. There's no scenario in which both are right.
It's like having two perfect rulers measuring the same room, and each one gives a different result.
Exactly. A ruler based on the original house plan says the room is 6.70 meters. The other, a laser measuring tape used today, says it's 7.40 meters. The problem is that both tools are considered perfect.
And for a long time, the bet was that the error was in the most recent method, the one using Cepheids. The hope was that James Webb would find this error.
That was the great hope of many, but Webb did the opposite. Adam Rees, the Nobel laureate who led this work, used Webb to recalibrate everything. And he was categorical. He said, "We can rule out measurement error as the cause of the Hubble tension with very high confidence."
Wow. So Webb didn't solve the problem. It confirmed that the problem is real, the measurements are not wrong.
Which means that our model of the universe is what's wrong.
It's the only conclusion left.
That's right. The two different answers the universe gives us are actually real. The expansion rate measured in the past is different from the rate measured today. And as the new study showed, the rate today is also not the same in all directions.
To keep receiving detailed dossiers like this, make sure you are subscribed.
And that brings us to the trillion-dollar question. Why? If our model is broken, what broke it?
I imagine the theorists are pulling their hair out. What is the main suspect?
The main suspect is the most mysterious component of our universe, dark energy. That invisible force that's accelerating the expansion. For decades, our model assumed that dark energy was a constant, smooth, uniform, and unchanging.
What if that assumption is wrong? What if dark energy isn't so constant after all?
Exactly that hypothesis. What if dark energy is stronger in some parts of the cosmos and weaker in others? What if it has clumps or varies over time? That could, in theory, explain why we see different rates of expansion. It would be pulling more strongly in some directions than in others.
The implications of this are hard to digest. If the universe is not homogeneous, that means the laws of physics we measure here might not be the same somewhere else.
That's the most radical consequence. Our understanding of physics might be only local, valid just for our cosmic neighborhood. The source material we analyzed even uses dramatic examples. In a very distant region, gravity could work the other way around. The speed of light could be different.
Reality itself would follow different rules. It's no wonder they use the word crisis. That overturns the cosmological principle.
Yes, a principle that dates back to Copernicus. The idea that we are not special. The Earth is not the center. The Sun is not the center. Our galaxy is not the center. Every place is just like any other place.
And now data from Webb is whispering a dangerous alternative. Maybe, just maybe, our place in the universe is in fact special in some way.
What we have in the end is monumental conflict. On one side, the cold and precise data from James Webb, showing us how the universe is. On the other side, a century of theory built on how the universe should be.
And the theory is losing. The central question, then, remains open. Why does the universe behave this way? Is it dark energy's fault, or are we facing something completely new?
This is the frontier of cosmology today. We are in uncharted territory, and every new image from Webb could hold the next clue or the next paradox.
That leaves me with one last thought. If the laws of physics are not actually universal, and if our location in the cosmos is special, what does that mean for the search for life elsewhere?
It's a thought-provoking idea. It could mean that life as we know it is only possible in regions with a very specific rate of expansion and a very specific dark energy density, like ours.
Making life a cosmic anomaly and not an inevitability.
Exactly. The answer to the Fermi paradox, where is everybody, could be that everyone needs a universe that behaves like ours. And maybe those places are incredibly rare.